Every 10.5 hours, a planet completes an entire year. It is so close to its star that one side never sees darkness and the other never sees light. The sunlit half is not made of rock in the way you might picture it. It is a sea of liquid stone, glowing orange and white, stretching from horizon to horizon with no shore and no solid ground anywhere. Everything we know about planets like this says they should be bare, stripped, completely exposed to space. But this one is wrapped in a thick blanket of gas that no one can fully explain. The planet is called TOI-561b. It orbits a star about 280 light-years from Earth, a star slightly smaller and cooler than our Sun. But the distance between planet and star is almost nothing. And if you shrank the inner solar system to a tabletop and laid Mercury's orbit out as a dinner plate, TOI-561b's orbit would fit inside a coin at the center. One face of the planet is permanently aimed at the star. The other is turned away forever. No sunrise, no sunset. Just a sharp line dividing a hemisphere that glows white-hot from a hemisphere locked in total darkness. That bright side does not just reflect light, it generates its own. The surface is molten, and at around 2,700 degrees Celsius, it radiates visible light the way iron radiates in a forge. If you could look down on this world, you would see a glowing ocean of rock shifting slowly as currents of magma rise and sink beneath the surface. The dark side should be cold enough for that magma to freeze solid. And between the two halves, there should be nothing. No gas, no wind, no energy moving from one side to the other. That expectation comes from what we see in our own solar system. Venus, large and wrapped in dense cloud, holds a crushing blanket of carbon dioxide. Earth, slightly smaller, holds its thinner atmosphere with its gravity. Mars has lost most of what it once had. You can see the remnant in orbital images, a faint blue haze clinging to the horizon. And Mercury, closest to the Sun, has essentially nothing. Spacecraft images show a bare gray surface fully exposed to space. Less mass and more heat means less atmosphere. TOI-561b sits at the extreme end of that pattern. Twice Earth's mass, but 40 times closer to its star than Mercury is to the Sun. It receives over 5,000 times the radiation Earth does, be enough to keep its entire dayside above the melting point of basalt. And its star is roughly 10 billion years old, twice the age of our Sun. Whatever atmosphere this planet started with has had twice the lifetime of our solar system to be blasted away. And yet, in May of 2024, a team led by Johanna Teskey at the Carnegie Institution for Science aimed the James Webb Space Telescope at this planet and held it there for 37 hours. Picture the telescope hanging in its orbit, its golden mirror locked onto a single point of light, watching as this tiny planet swings around its star nearly 4 complete times. Each time the planet passes behind the star, the system's glow dips. Each time it swings back out, the glow returns. That rhythmic dip and rise is how the team read the dayside temperature. Well, what they found did not fit. A bare rock should have measured around 2,700 degrees Celsius. The telescope read closer to 1,800, still hot enough that rock pours like water across the surface, but 900 degrees cooler than predicted. 900 degrees is the difference between flowing lava and a summer afternoon. Something was catching the heat before it reached the telescope. The team tested every alternative. Maybe the magma ocean was circulating heat to the night side. But picture a river of glowing lava crossing that sharp line between light and dark, its surface dimming from white to orange to red, then hardening into black solid rock like a frozen riverbed. Once the rock sets, the flow stops. Not enough. Maybe rock vapor. Stone turned to steam, a shimmering in a thin haze just above the glowing surface. But the models showed that could explain only a few dozen degrees. nowhere close. That left one explanation: a thick atmosphere loaded with volatile compounds, water vapor, carbon dioxide, oxygen, dense enough to drive winds across the terminator, pushing heat from the bright hemisphere to the dark, dense enough that water vapor in the lower layers would glow faintly in infrared as it absorbed energy rising from the surface, filtering the planet's light before it could reach the telescope. Dense enough to hold silicate clouds, bright layers of condensed mineral particles suspended in the sky, bouncing starlight back into space. Angeli Piet from the University of Birmingham, a co-author on the study, was clear: nothing else matched. But finding the atmosphere was not the hard part. Explaining how it survived was. In our solar system, stellar bombardment stripped Mars of nearly all its air. You can see the result: a rust-colored desert under a dusty pink sky so thin that surface pressure is less than 1% of Earth's. TOI-561b has endured far worse for twice as long. By every model, it should look the same. The answer is that this atmosphere is not a survivor. It is something the planet builds fresh, continuously, from the inside out. Picture the surface again: molten rock churning in a slow boil, bright magma rising, darker magma sinking. Dissolved inside that liquid rock are volatile compounds, gases held under enormous pressure, the way carbon dioxide stays dissolved in a sealed bottle. As the magma rises, the pressure drops. The gases escape, and breaking the surface in bursts and plumes, rising into the sky. At the same time, convective currents pull material back down, reabsorbing gases into the interior. The atmosphere is not a fixed shell. It is a living exchange. The magma feeds the sky feeds the magma. The cycle runs without pause. Tim Lichtenberg from the University of Groningen called it a wet lava ball. Not wet with water. Wet in the sense that the interior is drenched in volatile material, far more than Earth ever held. The star keeps ripping gas away from the top. But the reservoir below is so vast that it does not matter. The atmosphere is not old. It is perpetually new. This also cracks open a second puzzle. The planet's density is noticeably lower than Earth's. Part of the answer is origin. Its star belongs to the thick disk of the Milky Way. What that if you could see the galaxy edge on, you would see a thin, bright stripe of younger stars through the middle, where our sun lives, and above and below it a wider, puffier band of older, dimmer stars. That is the thick disk. Stars there formed with less iron, and their planets carry lighter rock. But a thick atmosphere also inflates the planet's apparent size as it crosses in front of its star, pushing the measured density down. The atmosphere solved two puzzles at once. TOI-561b formed when the universe was less than 4 billion years old, from a simpler mix of elements. It may be a surviving example of what the earliest rocky worlds looked like, not a fossil, because it is still active, a living relic. And the most striking connection is with our own world. Every rocky planet in our solar system was once molten, our Earth included. 4.5 billion years ago, our planet was a magma ocean under a sky choked with volcanic gas. The water we drink and the nitrogen we breathe came from rock, bubbling up from a molten interior exactly the way gas rises through the surface of TOI-561b right now. The difference is that Earth cooled. The crust hardened, rain fell for millions of years, oceans filled, the atmosphere settled. TOI-561b will never cool. It is locked too close to its star. The process Earth finished is the process this planet will repeat forever. The study, published in the astrophysical journal Letters in December of 2025, is only the beginning. The team is now mapping temperatures around the entire planet and identifying the atmospheric gases. If it turns out to be mostly water vapor, and the planet likely formed past the frost line, that boundary where temperatures drop low enough for water to freeze and spiraled inward over time. If carbon dioxide dominates, the story shifts. Each answer reshapes the question. TOI-561b was supposed to be simple, a small hot rock baked clean by 10 billion years of starlight. Instead, it turned out to be a world that refuses to go quiet. It rebuilds itself from the inside out, one eruption at a time, and it has been doing so for longer than our sun has existed.